over the square root of 1 minus v squared over c squared. And what it does is makes it blow up. The equation blows up. You get an undefined values. Now, so the faster you're moving, the more energy you have, right? Well, energy is equivalent to mass. So the more energy you have, the more you read it. I saw you. You did too. The more energy you have, therefore the more mass you would have. So the closer you get to the speed of light, the more massive you become. And when you get near the speed of light, you then become infinitely massive and infinitesimally small. So I guess you'd be denser. Again, what if you could you go over the speed of light? No, because you can't be more than infinitely massive. No. The last thing that can happen, that would be the third one. Length contraction, mass expansion, time dilation. Simultaneous events just is how we got to length. That's part of length. Since events are not spontaneous to all frames of reference, then we can have a change. Time dilation, as you get closer to the speed of light, time changes. It actually runs slower. Now, how can we imagine that? How can we figure that out? Let's say you have a box. Okay? In my box, I'm holding here, I have a pulse of light, a little ball of light. Now my box is mirrored on the inside. Okay? So if I have a box of light, or a box of mirrors, and I've got a little ball of light in there. You ever been to like an airport bathroom or something like that where you got mirrors on both sides? And you look in the mirror and you can like see, keeps going back and forth, back and forth, back and forth. The light's just doing that, going back and forth, back and forth. So think of the same thing. So I've got a little ball of light and it's going to bounce up and down, right? It's just going to go boop, 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 boop between the mirrors. Doesn't lose any energy, so it's always going to do that. So I'm sitting here, what do I see? I see the light beam, or the light ball going up and down, right? Sure, it's a one-way mirror. It's a thought experiment. Can you actually do this? No. Because you'd have to use one photon of light, and it's tough to get one. But can you imagine what I'm talking about? Okay, so I've got a ball of light, so it's exactly like this. All right? White. All right, so it's exactly like this. This is what I see bouncing back and forth in my box. Going straight up and down. I'm holding it just like this. What do you see? You see the ball going up and down. Okay? It's a thought experiment. No, you can't. If I could see at the speed, if I could discern things at the speed of light, yes, I could. I got really good eyes. Watching it like this. Like watching a tennis match. But this is what you see. Okay? Now, as I start to travel faster, okay? Because I'm the guy with the light box. As I start to travel faster, what do I see my ball of light doing? I'm traveling in space, going that way. I'm in my car with my box of light. And what do I see my ball doing? Just going up and down. What does someone from outside my car see the ball doing? Again, it's doing this, right? So if I'm inside my car, I see my ball of light doing this, back and forth. It's traveling that distance. I know my ball of light is traveling at the speed of light, so I know its speed, so I can then measure time. Because I know that speed is distance over time, and if it's the speed of light, distance over time, or time is the distance it travels divided by the speed of light. I wrote it down. All right, that's our old friend. You know. I'm extending the experiment we just did, the thought experiment we just did with the ball in the car and you seeing it, to, okay, something traveling at the speed of light. So by knowing the distance that my ball of light travels, according to me, I can then figure time, right? So time goes by, for me, at a normal pace. Now, the guy standing by the side of the road watching my car near the speed of light going by, wow, what does he see my ball doing? Yeah.
Hey, we're so logically smart that you can't.
This is why Einstein's theories were so hard for people to accept, because they have no imagination, I swear. My car travels in space. Okay, I'm in my magical car. First I'm talking about a ball of light and you're buying that one. Now you're arguing because my car can't drive in space. Hmm? Yeah. C is a constant. The universal constant is the speed of light. Those of you in chemistry right now should realize that because we use that all the time. Yeah. So the observer sees my ball of light travel that far before it bounces back. Right? So he sees it travel farther. Just like, backing up to the beginning of the class, if I'm holding my ball and I'm throwing it up and down, the observer by the side of the road sees my ball travel farther than I do, right? He sees it move along the road. But in this case, we're talking about much faster speeds. Again, time is distance over the speed of light. According to the person observing me, speed of light's the same. What happens to the distance? Distance is now, the ball of light has traveled a greater distance. So if it's traveled a greater distance, if the top becomes, if this number goes up, what happens to that? It also goes up. So my observer by the side of the road, or side of space, or whatever you want, sees the ball of light going like this, and more time passes for that person than it does for me. Because I see my ball of light going up, straight up and down, he sees it traveling a longer distance. If you're at near the speed of light, and we can't travel that fast, the famous paradox is if you take a pair of twins, put one on a spaceship, put them on a spaceship and send them off and bring them back a long time, according to him, a year later, his twin is dead for a long time because so much more time has gone for the guy who's standing still than the one who's traveling at the speed of light. Now that's kind of like a form of time travel, and you did that reading. Yes, they have. Because what is the fastest man-made object that we know of? Nope. The space shuttle. The space shuttle travels at like 10,000 miles an hour. And there is they've taken atomic clocks, one on Earth, put one on the space shuttle, compared to when they get back, and there's a difference. Not a big difference, but there is a difference. And that's one of the main physical proofs of it. Fractions of a second. So, yeah. But if you then would travel faster, then the time difference would be more. We just can't travel any faster. Yes. If you had a radioactive material, and they've tried this, and it works. If you have a radioactive material that has a very short half-life, and you want to make it last longer, you can put it in a centrifuge and spin it at a very, very high speed. Since it's moving very, very fast then, it'll actually have the same half-life to it, but to us it appears longer. Really fast. Well, they can't make it decay faster. They can make it'll decay slower according to us. According to it, it's still decaying at the same rate. But to us, I don't know if they actually do it with anything for real purposes. They could. If you had something that was important for cancer research or something, who knows? Yeah, you'd have to really have a lot. It's too big. It's an idea. All right. Now, you just really need to be exposed to some Einstein. I mean, it is something you have to realize that, will you all get it? No. Well, I got all kinds of videos, but we might look at one later when we look at general relativity. General relativity is harder to figure out. There's been a lot of quotes about Einstein and understanding Einstein. One was it was back in the 20s or 30s. There was a guy by the name Eddington. He was brilliant, and someone in an interview asked him. Now I understand there's only 3 people in the world that understand Einstein. And the guy sat there and went, and the guy goes, interview him, goes, what's the matter? He said, well, I'm trying to think of the third one. Because he would be one, Einstein would be the other, and he couldn't forget it. All right. What should you do now? Let's actually work this time. Get your stuff done. Get her turned in.